Hi everyone, I'm Rajesh Sridhar Bhatt. I'm working as a senior data scientist at Walmart Global Tech India. Today I'll be covering detecting and recognizing arbitrary shape text from product images. So this is how the agenda looks like. So initially I'll give an overview of text extraction. Later I'll talk about text detection techniques and then go to the text recognition train data preparation task. Later, I'll talk about different models for text recognition to start with CNN CTC model, then attention-based model. Then basically cover spatial transformation networks. That's basically for improving the text recognition accuracy when there is arbitrary shape text or curved text. Then I'll talk about model accuracies on different settings on different data sets. Then at final, I'll be talking on training and deploying the models. Yeah, in order to extract the text, so basically we need to know where exactly the text is present on the product image. So that is nothing but the text detection task. So after text detection task, we have the bounding boxes that is coming from the text detection model. And once we know where exactly the text is present on the image, so we can crop those regions and we can send those cropped regions to the text recognition task. So after the text recognition task, we have the raw text that was present on the product image, basically. So you can see the example below as well. So given a product image, text detection is done, and we know where exactly the text is present on the image. So you can see the bounding boxes over there. And once we have the bounding boxes, we crop those regions and send it to the text recognition model. And finally, we have the raw text that is coming out from the text recognition model. So I'll briefly talk about the use cases that we are trying to solve in Walmart. So one of the use cases seeing if there is any offensive content in the product image or not, right? So we definitely don't want to show those kind of images in the .com site, right? And other use cases are sometimes it so happens that the product catalog is not clean, and sometimes few of the attributes go missing, right? So in that situation, so we extract the text from product images and then do a attribute extraction on top of it. So attribute could be like brand or ingredients, something, right? So like that are like couple of use cases which are like specific to retail and e-commerce. So apart from that, there are like multiple use cases where one can use text extraction. So one of the example is like let's say social media content monitoring, right? So if you consider Facebook or any other social media platforms, there's so much content that is being uploaded on a day-to-day basis, right? And manually monitoring all those things is like a very difficult task. So we can have text extraction in place. Whatever images uploaded, we try to see what content is present in that. Is it offensive? Is it against something, right? So we can extract those information automatically and try to automate this task. So these are like a couple of use cases with text extraction. So now I'll briefly talk about the text detection task. Yeah, so in text detection, I'm actually referring to a paper which was published in CVPR 2019. So that was from Clova AI. So Youngmin et al., they came up with a paper called Character Region Awareness for Text Detection. So basically, the text detection is achieved at a character level instead of treating the task at a word level, right? Unlike many of the text detection models that are readily available. So this is slightly different since it's achieving the text detection task at a character level and then trying to combine the information and then form a bounding box on a word level. So it's a segmentation task. So when it's a segmentation task, then the well-known architecture is like UNet. So that's pretty famous in medical image segmentation tasks. So here also for the text detection, the architecture looks pretty similar. So we have like BGG16 batch normalized version of BGG16 as a backbone in the UNet architecture, and like few upsampling blocks and definitely like skip connections, right? So as you can see, given an input image, finally the output from the model is the region score and affinity score, right? So region score is mainly for telling us that where exactly the text is present, the character is present in the image. right? And the affinity score is mainly for grouping the characters, saying that given two characters, are they belonging to same word or not, right? So basically, these are nothing but the masks that are coming out from the segmentation model. So in any typical segmentation task, we have an input image and we try to come up with a appropriate mask for that, right? Basically, the object that is being in focus, right? So we'll be getting the mask over there. Here, the object that is in focus is nothing but the text. Okay, so in segmentation task, since I told that we need mask, in the training phase as well, right? We need the corresponding image. We need the image and the corresponding mask for that. So basically, since text detection model is giving region score and affinity score, we need mask for both of these tasks. So as a training data, we have character boxes with us. As you can see in this image, we have the character boxes for piece, word piece, right? And for each of the characters, we have the detection boxes, right? So that is the ground truth that is available to us. So this is open source data that is called syntext data. Okay. So once we have this character boxes, we generate affinity boxes, and finally we arrive at region score ground truth and affinity score ground truth using this affinity boxes and character boxes. Now we'll see how we get the affinity boxes from the character boxes. Take the two boxes from the two consecutive characters, that is P and E, then join the diagonals, right? Basically this part, right? We are after joining the diagonals for both of these characters P and E, right? Then we get these triangles. Then find the centroids of these triangles and connect all these centroids. Right? So that is nothing but a affinity box. Right? Affinity boxes tell that are these two characters, are they part of same word or not? Right? So if you look at this image piece, right, and there is also a word that Y that is written, WHY. There is no affinity box between the last letter E and the initial letter W, right? Because they are part of two different words. Right? So there is no affinity box over there. So once we have the affinity boxes and character boxes, right? Then we take a 2D isotropic Gaussian, right? And we have a box, a character box or affinity box. Then we try to warp this 2D isotropic Gaussian into that particular box. That is nothing but a we apply a perspective transform and then arrive at a transformed 2D Gaussian. Right? So this transformed 2D Gaussian is nothing but a mask for me, for each of the characters, and also for the affinity between the characters. Okay. So this is the input image. Ignore the boxes for now. P is nothing but an input image for us. And the ground truth for this image is the region score ground truths and affinity score ground truths. So this is the input and these two are the outputs. So these are basically the mask. Typically in segmentation tasks, we have like a binary mask, but in this case, we have a continuous like 2D Gaussian as a mask over here. Okay, and the loss function is also, since it's continuous, so will be, so in the paper it's mentioned that they're using mean squared error as a loss function. Okay, you can refer to the paper. I've given the reference here. You can refer to the paper offline and get more details on that. But I hope you got an overview of how text detection is achieved now. Okay, so this is the sample output which I've taken from the paper itself. Given the input image, right, that is on the top, you can see the region score and affinity score corresponding to that, right? So if you take the example of seafood and shack, right? So there is no affinity score between the last word, that is D, and the first word, that is S, because these two letters are part of different words, right? So there is no affinity score here. We can see a gap over here, right? There is no mask over here, okay? So once we have the region score and affinity score, right, we can combine these two scores and then we can use the functionalities from OpenCV, that is connected components and minimum area rectangle functionalities from OpenCV to finally arrive at a bounding box, right? So as you can see in the top, you have a bounding box for each of the words, right? Yeah, so this was like published in the paper itself. I have taken the same. Now we'll see on the product image how the results look like. Okay, so I have taken two sample products over here. So as you can see, this is the character scores, right? Basically, the character scores are present and using the affinity scores also, and we finally arrive at bounding box for each of the words in the product image, right? So only important thing I would say is like there is a craft that is written on the lid of this product, right? So even if it's not in a regular fashion, if you look at sandwich and spread, right? So they are like, I mean, it's easy to read, right, for human eyes as well. But there is a word craft that is written on the lid, right? Even if it's in a slightly slanted fashion or in a different perspective, we are able to detect those things. Now the challenge is in like, okay, we are detecting it, but how do we recognize it, right? So we'll see, like we'll see through the slides. We'll see like how this can be achieved using spatial transformation networks. Okay, so next task is yeah. Once we have the bounding boxes, now next task is to do the text recognition. So we'll see in detail how the text recognition task is achieved. Yeah, before diving deep into the techniques, I would like to focus on the data generation part, training data generation part for the text recognition task. So basically, we are using the text product titles and descriptions and trying to synthetically create the images using that. Okay, so we are using a library called Syntext. So it's like given the plain text, right? The description or a title, product title. So we sample unigrams and bigrams. We take one word at a time or two word at a time and try to synthetically create the image out of it. Okay, so we created around 15 million images using the product titles and descriptions, and a lot of variations during the text image generation, right, was included in the data set. So the variations include like change in font styles, change in font sizes, different colors, different backgrounds. A lot of variations were included in the training set. Okay, because in the product images also the text is not straightforward. Like we have a lot of variations in the product image itself, right? So in order to mimic that, we included those variations in the data generation process as well, right? So finally, like we had 92 characters in the vocabulary, which includes capital and small letters, numbers, and special symbols. Because we included special symbols because there is a lot of special symbols that goes into the product image kind of a setting. Right? Yeah, the kind of data that is generated, right? It all depends on the end task we have. So in this case, it was like extracting text from product images. So we took titles and descriptions and synthetically created the data. Right? Let's say we are trying to solve the captcha, right? Then the type of text that goes into the training set in creating the training set is totally different, right? So it could be random letters followed by a few numbers or something with a strike through line or something, right? So the kind of data set that we create totally depends on the task that is in hand. Right? Yeah, now I'll talk on the different techniques. Yeah, to start with, we developed CRNN CTC model for text recognition. So I'll not talk in detail on this because this was already covered in my previous talk that happened like few months back in Spark AI Summit. So you can, it's already available in YouTube. So you can look in YouTube for text extraction Spark AI Summit. You should be able to see the detailed explanation on CRNN CTC networks. Also, a blog is published in Weights and Biases. So here is a link to the blog, and also you can just scan this QR code to go to the blog, and you can take it offline. Okay. So we started with CRNN CTC model. Then we saw that it was not performing well if the image is a little blurry, right? Yeah, after the CNN CTC model, right, we are not getting good accuracies if the image was blurred and all, right? So that's why we went ahead with attention mechanism in place. So basically, image is passed to a CNN model. Then after passing to the CNN model, we get the features out of it. And then this visual features are fed to the LSTM encoder. Okay, and then from the LSTM encoder block, we get hidden states at every time step, and these are used in the for the attention mechanism, right? So weights are given to this LSTM hidden units from the encoder block, And finally, this attention scores are utilized to focus more on certain part of the image, and then the decoding is done in the LSTM decoder block. Okay, the intuition here is like, let's say we are trying to extract the letter F, right? So we have forum over here, right? So the image contains the word forum, right? Let's say we are extracting the letter F. Okay, now I mean the focus should be morely like mainly on the letter F, right? When extracting the letter F, so we need not focus on the entire image, right? So that is the intuition. So attention mechanism takes care of that, and the weightage while extracting F, right? Uh, Weightage would be given more near the region where F is present. Okay, and similarly for the other characters. So this is done in a generative fashion. Okay, compared to a CRN CTC model, right? So that was done in a discriminative fashion. So this is encoder decoder framework, and hence that is like it's achieved. The predictions are in a generative fashion. Okay, so one can also use beam search here to make the predictions better. Okay. So basically, in the decoder block, for every time step, what we have is softmax probabilities over the vocabulary. So as I said earlier, like we had like 92 characters in the vocabulary. So for every time step, we get the softmax predictions over the vocabulary. Okay, then using that, we can come to a conclusion like what letter we are trying to get in that particular time step, and then we can totally get the predictions out of it. Right? Since this is done in a generative fashion, we can go ahead and use cross entropy as a loss function. Okay. Yeah. So later we saw that product images with curved text, right? So we were not able to do pretty decent when extracting if the text contained arbitrary shaped or curved text. Okay. So here the use case was like offensive text classification, right? On the T-shirt images, there are like few offensive text, and sometimes it happened that the text was in a curved fashion. Okay, and uh, if you look at the left image, right? So there you can see the brand Happilo is like written in a curved fashion, right? So we were facing some challenges in recognizing them with the attention or CRN and CTC network. Right? We were able to do pretty decently on detection tasks since that was achieved through character level segmentation. But on the recognition side, the model was not doing that great. So we went ahead with spatial transformation networks. So spatial transformation networks is nothing but it's a learnable module. So its aim is to increase the spatial invariance of convolution neural networks in a computationally and parameter efficient manner. Right. So let's say we have a CNN LSTM attention based model, right? So we can plug this model STNs just before the CNN module, and these are learnable modules, and basically they try to learn affine transformations, right? So as you can see in the image here, given the input image that is in a curved fashion, so after the spatial transformation network that is being applied, we have a rectified image. So the word moon, previously it was curved, then we have a rectified version of the word moon over here. Right? So once we have that, the rectified image or a normalized image, right? So rest all process remains the same. So we can feed it through a CNN LSTM attention based model or a CRNN CTC based model, right? So basically, spatial transformation networks helps in like transforming the curved shape or arbitrary shaped image or a text to a normalized fashion, right? So that is the main advantage of having spatial transformation networks. Okay, so as you can see here, so I have put down the model accuracies, different models on different data sets. So till ICDR 13, so the data sets contain regular shape text only. There is no much variation in the test data. But after from the ICDR 15, which is highlighted, right, the last 4 rows basically. So that contains samples which include a lot of variations, basically arbitrary shape text or curved text, those kind of variations, right? So when I say accuracy over here, right, so if you look into the right, so let's say the ground truth is hello and the predicted is hello, if there is an exact match, then the score is given as 1. So even if there is a mismatch in a single character, right? So the score is treated as 0 here, right? Okay. Now you can see on the regular shape text, right? With CRN and CTC models on, let's say, IIIT 5K dataset, right? So the accuracy was 81.6, and LSTM attention based also was giving pretty similar ones, similar accuracy basically, right? And if you go to the ICDR 15 or CUTE dataset, right, you can see that CNN CTC or CNN LSTM model without spatial transformation had much lower accuracy. So the accuracy was around like 65 to 66%, right? But if you see with spatial transformation networks, right, so the accuracy is like 20% increased now, right? So it's around like 85% accurate now, right? And similarly, same thing holds good for ICDR 15 or SVT perspective dataset, right? So you can see that spatial transformations have definitely helped us in recognizing the arbitrary shape text, and that is like clearly evident in the accuracies that are presented over here. Okay, finally, like coming to the training and deployment part. So as I said earlier, like we created 15 million images. And so if we load everything into memory, that would come up to like 690 GB, given that the image size is like 128 into 32 into 3. 3 is nothing but saying that it's a color image, right? So we're using data loaders from PyTorch. So basically, it's achieved in a generative fashion. Generators are used, and instead of loading everything into memory, only a single batch is loaded into memory, right? And the training is done accordingly. The training was done on V100 GPUs, 4 GPUs parallelly. And once the model was trained, so we deployed these models on machine learning platform that is internal to Walmart. Initially, we had like separate deployments for text detection and recognition task. So later we saw, I mean, those separate API call needs to be made to extract the final text, right? So it's wastage of 2 API calls means like, sending the image twice over the network. So network latency is also counted in the overall extraction, right? So that's why we clubbed both text detection and recognition model in a single deployment. And so it's deployed on our V100 GPUs, and the prediction time for each image is roughly around 0.45 seconds. Okay, so yeah, this was on the training and deployment, and this is a team behind the project, myself, Rajesh Bhatt, and then I have my colleagues, Pranay, Anirban, and Vijay, who are part of this project. Yeah, I hope you all got an idea on how to tackle text detection and recognition problem when text of arbitrary shapes are involved, right? So given the limited time, I tried to give an overview of different techniques. I hope that was useful. Yeah, the code and sample code for the content of the talk and the PPT is available in the GitHub link here. So you can refer to the GitHub link, or you can scan the QR code. And if you have any questions, please go ahead.